This video demonstrates an SDN-based DDoS mitigation mechanism that was developed by the Nekoma project. First of all, we will discuss the background. As you know, large-scale DDoS attacks took place on the internet recently. The volume of such attacks is increasing and approaching to a few hundred gigabytes per second in a single attack. The reason why the volume is increasing is because amplification-type DDoS attacks are becoming popular in recent years. Let's look at the mechanism of this type of attack in detail. We will show you the mechanisms of DNS amplification attacks, which are a common amplification DDoS attack. In this DDoS attack, attackers use open resolvers as amplifiers of the attack, which are vulnerable DNS cache servers. This sort of DNS cache server can reply to DNS queries which are sent from the outside of the networks, and this behavior is unusual. Legitimate DNS cache servers are limited to clients that are located on their network and are not open to external clients. In the first step, attackers send DNS queries to the open resolvers. The open resolvers' IP addresses can be collected by simple scanning. The attackers easily acquire the information. The source IP addresses of the queries are spoofed as the victim's IP addresses in order to lead reply packets to the victims. In the second step, the open resolvers send reply packets to the victims. The size of the packets are relatively bigger than the original queries. This means that attackers just send small-sized packets to the open resolvers and easily generate large volumes of attack traffic. In large-scale amplification attacks, the source hosts of queries are widely distributed all over the world. The amplified response packets are forwarded to the victims. The attack traffic saturates the victims. Finally, the victim is unable to provide network services, such as web services, due to the attack traffic. Moreover, the traffic constrains the internet backbone and the ISP's links among the open resolvers and the victims. Accordingly, the attack is causing problems not only for the victims, but also for any entities on the internet. The traffic volume is approaching over hundreds of gigabytes per second in modern times. Therefore, it is necessary to effectively mitigate the attack on the whole of the internet through collaboration among entities on the internet, not only on the victims' networks. The following is the research and development background. The main problem for DDoS attacks is that such attacks constrain links on the internet. It is hard to defend against DDoS attacks on a single network. Attack traffic can potentially be transmitted from anywhere in the world. Next, I will provide a demonstration of an SDN-based DDoS mitigation mechanism that was developed in this project. In our demonstration, we present an SDN-based DDoS mitigation against the attacks. Also, we show a pipeline from collecting DDoS data, detecting attacks, sharing the detected information, and mitigating the detected attacks by utilizing the proposed mitigation mechanism. Let's take a look at the scenario overview. In this scenario, there are 4 entities: an SDN switch, a detector, the Nekoma platform, and a controller. First, the detector collects traffic information from the switch using S-flow. The detector analyzes the traffic. If a DDoS attack is detected by the analyzer, the information will be posted on Nekoma. Nekoma is a threat-sharing platform developed by the Nekoma project. The platform has a timeline like Twitter for sharing security information among operators and bots. In this case, the detector works as a bot and automatically posts attack information on the Nekoma timeline. A bot can post and also work as a timeline watcher. On the controller, a watching bot is residentially running on the controller. When the watching bot receives threat information from Nekoma, the bot initiates mitigation processes against the attack through the controller. The controller installs packet filtering entries on the SDN switch by using OpenFlow protocol. Finally, malicious traffic is discarded by the filtering entries on the switch, so that only legitimate traffic can be forwarded. We can improve resilience against the DDoS attacks by repeatedly executing this cycle. The mitigation mechanism can be applied on ISP or consumer-scale networks. Next, we will explain the demonstration platform for the scenario. We integrated the mitigation mechanism on a small emulation environment. The platform is comprised of 3 physical servers, 8 virtual machines that are running on the physical servers, and 1 OpenFlow-capable virtual switch. These controllers are dynamically configured using Ansible playbooks. The figure shows the architecture of the platform. The 3 hypervisors are connected via a physical switch. 7 virtual machines are running on the hypervisors and internally connected with the other machines. Now, we are ready for demonstrating the scenario. First, we set up the demonstration environment using Ansible scripts. In this window, we execute the scripts on the master node of the platform. The scripts install hypervisor and requirement software. Next, the master node prepares VM images, propagates the images to the hypervisors, and installs software for each VM. Let's take a look at the initial timeline of Necomatter. At the moment, there are no posts on the timeline. Next, we will show the initial OpenFlow table of the switch. The table entries can be found by using the ovs-of control command on the switch. At this time, 2 flow entries have been installed on the switch for forwarding packets between 2 ports. We follow the scenario step by step. First, the attacker host sends spoofed DNS queries to 3 open resolvers. Second, the resolvers reply with response packets to the victim host through the switches. This script initiates the attack. At the moment, the switch is forwarding massive attack packets from the resolvers to the victim host. Actually, 1 pre-installed forwarding entry matched the attack packets. Next, starting detector function. The detector observes the network traffic through SFlow and analyzes the traffic. If the analyzer found malicious activity in the traffic, the detector posts attack information on Necomatter. In this case, we adapted a simple threshold-based detection algorithm on the detector. On this screen, the left side is the terminal window on the detector, and the right side is the Necomatter timeline. First, we start the detection program by using these commands. After starting the program, detected information will appear on the Necomatter timeline. Each post has only 1 attack source IP address. In the end, we got information on 3 malicious IP addresses in the timeline. The posted attack information will be used by another bot to initiate a mitigation. The bot is getting the information from the timeline. After that, the bot initiates mitigation for the attack on the SDN switch. This command initiates the mitigator bot on the controller. The installed mitigation entries appear on the flow table. 3 mitigation entries have been installed on the switch. We evaluated the additional latency caused by our mechanism and the time between when an attack is detected on a detector and when a mitigation entry is installed on the OpenFlow switch from the controller. First, we measured the latency of the mechanism using ICMP packets. The results showed that the mitigation mechanism caused only 0.397 milliseconds of additional delay. Thus, the additional latency can be considered short. Next, we evaluated the time to recover metric. This time is the reaction time between when an attack is detected on a detector and when a mitigation entry is installed on the OpenFlow switch from the controller. The evaluation results reveals just how quickly attacks have been mitigated by the proposed mechanism. The time is calculated by Tm minus Td. Td is the detection time on the detector. Tm is the mitigation time when the mitigation is initiated by the controller. We measured the time on our platform 50 times. This box plot shows the results. The average time to recover is 10.8 seconds. This reaction time is considerably shorter than the duration of common DDoS attacks. In this video, we showed an SDN-based mitigation mechanism. Furthermore, we demonstrated a security pipeline from data collection to attack mitigation with that mechanism.